It's now time for us to engage in some scientific discussions. We have 4 students to deliver enthralling talks on various topics. We request the student speakers to strictly stick to their time slots. The presentation will be for 10 minutes, followed by 5 minutes of question and answer session.
Our first speaker for today is Avvaru Akshay Kumar, who is here to talk about the Riemann hypothesis, on which many mathematical theorems were built, but yet why is it still remained unsolved? Let's hear from Akshay.
Good morning, everyone. So I kind of skipped the $1 million question part from my title, because after knowing what Riemann hypothesis is and how beautiful it is, it kind of seemed priceless to me. So I hope you'll appreciate the same with my presentation. So Riemann hypothesis has implications in many different fields like number theory in mathematics and string and quantum theories in physics. But I'm here going to talk about the main thing that it is intended to do, that is predict the distribution of prime numbers. So as we all know, prime numbers are the numbers which have factors as itself and the number 1. And any natural number can be represented as its prime factors. So something that we take for granted is the existence of infinite prime numbers, but in mathematics anything should be proved. And this was first proved by Euclid in 350 BC with a simple but elegant solution, where if you have a set of all primes, all known primes, then you'll have a number which is a product of all of these numbers. Then n plus 1, which is product of all of these primes plus 1, isn't divisible by any of these primes but leaves a remainder when you divide it by them. And hence, there should be another prime which should be dividing this new number, and if there are infinite numbers, there are infinite primes. So now we know that there are infinite prime numbers, but we should know how they are distributed on the number line. Okay, so here is a simple prime counting function where on the x-axis we have all the natural numbers, and on the y we'll be counting how many of them have we encountered as we go further. So at 1 we have encountered 0 primes, and at 2 we have encountered 1, and at 3 there are 2, and at 4 there's no increase, but at 5 there's 1 again. And if we go further like this, we have something called the prime number or prime counting function. So many mathematicians were wondering what could be the function that closely mimics this one, or is there a function that predicts the occurrences of primes? And one of them was Gauss, who had looked at 3 million prime numbers till 3 million and tried to find a function which is closely mimicking this one. And as he was studying logarithms at the same time, he came up with this function, x by log x, which kind of closely goes along with the same prime counting function, but still doesn't perfectly mimic it. So there are errors as it goes along, and this increases as we go further along. Okay, so Riemann hypothesis, that part that which I'm going to talk about, is mainly about how we model the error that is left out with this x by log x function. Okay, so before I get to that story, there are a few plots I need to explain, starting with this simple problem, which is called the Basel problem. So here there is a sum of infinite series, which is sum of inverse squares of all natural numbers. So this was proposed around some 17th century by Pietro Mengoli and was solved by Leonhard Euler in around 1750s. So if you are wondering what kind of significance that this had at the time, or mathematicians were in generally trying to solve solutions for infinite summation series, and this was one of them. But for giving you an example of how this might be important, let's say we have some like masses which are distributed like this, where you have mass capital M at the 0 of the axis, and you have equal objects of the same mass equidistant on the same axis. And if you want to calculate what is the gravitational attraction force experienced by this mass here, it would be by Newton's gravitational law, we'll have a summation of the inverse radius squares. So this is where I'm giving you an example so that you understand what kind of significance this holds. And Leonard, in a very elegant proof, has shown that this is equal to pi square by 6. And why pi comes in this is another beautiful story. But I'll not go into that. So Leonard, after proving this, he went on to prove this series for all other even powers as well. And he has shown for where the power is 4, 6 and so on for all even numbers, and given a generalized equation for this. Okay, so the next thing he did was to generalize this series function and called it as the zeta function, where zeta of s would be sum of all inverse powers of the natural number, of all natural numbers, inverse powers of with s. Okay, so after looking at it for all the even natural numbers, he looked at it for all other numbers. Like for example, what if s is equal to 1? And it is known that this series, summation of series, diverges to infinity. And what if s is less than 1, like s is equal to half? And again, this also diverges to infinity. And he has shown that this for any number which is lesser than 1 diverges to infinity, and is only defined and only converges when this s is greater than 1. Okay, so I guess so far you're following me. This is zeta function, and which is defined only for numbers which is s greater than 1. Now after this, Leonard had actually proven a very important thing, that is a link between the zeta function and the prime numbers. So we know that zeta function is a summation of all inverse powers of all natural numbers. And so let's say you have zeta of s as this, and now if you multiply this by 1 by 2 power s, what you have is summation of all even, same kind of series, but here you have only all even numbers as natural numbers. And when you subtract this from the actual equation, what you have is a series, the same series, but you get rid of all the even numbers in the series. And if you do with similar primes, like when you do with 1 by 3 power s, you will get rid of all the factors of 3. And if you do it further with all the primes, what you will have left with is 1. And now you can represent the zeta function as a product of primes and an inverse function of the same kind. Okay, so this showed that there is a good link between the prime numbers and also the zeta function. Now enter Riemann. So Riemann was kind of the founder of complex analysis, and what he's done here is taken the zeta function to complex numbers or complex plane. So as we know, complex numbers have this kind of a form where you have a real part to it and there is an imaginary part to it, and can be represented as x plus yi, where I is equal to under root of minus 1. So any complex number like 2 plus I can be represented in the complex plane with the real part on the x-axis and the imaginary part on the y-axis. Okay, so if you plug in such kind of a number into the Riemann in the zeta function, what you'll have is the same series with the complex number, and you'll have a complex output to it. Okay, so Riemann, what he did was he observed this for all the complex numbers, and in parallel with Euler, he had actually showed that the function is again defined in the complex plane, where the real part is greater than 1 and is again not defined in all the plane where the real part of the number is lesser than 1, which is in parallel to the Euler's finding. Okay, so now to look at this function in the complex plane, what we do is transform it by applying this function. When I say transform, what I do here is, let's say we have this point which we have looked at before, and we apply a function x square, and what we have is a resultant number which is actually 3 plus 4i. So this in this, with this transformation of x square, can be moved to 3 plus 4i. Okay, and when we do this with all the numbers, what we do is transform the complex plane based on this x square function. Okay, so when we look at this, so I've taken this up from a video of 3 blue, 1 brown. So here is an example of this is an actual complex plane, where you have -1, 1, and what happens to it when you transform it to x square? You have something like this. And to give you a visual representation, so this is how it gets transformed. So this is for x square, but what happens when you apply the zeta function? Oh, sorry. You have very beautiful curves coming up again with the zeta function, and Riemann has shown this, and what he has done after this is to not stop this function at the x is equal to 1, or the real part being equal to 1. He used a concept called analytical continuation, which was developed by Cauchy and again used and again developed by Euler and Riemann himself, and showed that this function can be extended further, or the domain of this function can be extended further into the plane where it is not defined. Okay, analytical continuation is again a concept we have to read about, but it has some rules, like the same function should be differentiable in the plane which is it being extended to. So now Riemann, what he has done is define this function in this plane as well. So it's not like the function is having new values or new definition in the same, but it is being assigned a value in this. Like we know, we must have seen this in our school, that the sum of all natural numbers is equal to -12. This is because of this Riemann's analytical continuation of the zeta function, where this s is equal to -1 is assigned the value -12. Okay. Now all of this is good. So what further we know is that Riemann has observed that this function never tends to 0 in the plane where it is defined, which is s greater than 1. But in the transformation, we have seen that some of the points actually go through the origin where it tends to 0. Okay, so Riemann wanted to find out what were these points where this function becomes 0, and some of them are the all negative integers, which is -2, -4 and so on, and all of these actually have a value assigned to them as 0. But these are called the trivial zeros, but Riemann has identified some more zeros of this function, almost 600 of them, and almost all of them, actually all of them, lie on this line where the real part of the number is half. Okay, so 600 zeros he has found manually and identified that all of them lie on this line where the real part of the number is half. Okay, so if we see this line on the transformation, we'll see the same transformation we have seen before. The line, when continued for infinity, goes through the origin a lot of times where it is 0. Okay, this is all good, but what about the prime number distribution that I'm going to talk about? Riemann, with another mathematician, has identified another function which is called the Riemann converter or Riemann-Siegel function, which when given a complex number outputs a harmonic series or harmonic wave. And what you see next is how it mimics or predicts the prime numbers. So when you take all the zeros on this line where the real part of x is half, all the zeros found by Riemann, and put them in this harmonic wave function, and the summation of all of these harmonic waves very beautifully gives you the errors which were seen by Gauss on the prime counting function. So this is a video which shows what happens when you plug in the first 200 zeros of this function into that harmonic wave function and add all of these harmonic waves. And as you go further, you see very nicely that this actually goes on closely with the prime counting function and only jumps at the points where on the number line you encounter the prime numbers. Okay, so this is what Riemann hypothesis is for the prime counting function, but there are definitely many other implications to it. Okay, so I want to end this talk in a circle. I want to explain how there was a series, the infinite series, which had no association with prime numbers, but Euler again saw that there was an association of prime numbers, but we don't know how it is. And you don't even have this function on a real plane, but now on a complex plane where you have imaginary numbers coming in, and also the function is not defined for a specific part of the plane, but is assigned and moved to the part where it is not defined. And now the zeros of this function are found, which when put in a harmonic wave function closely map the distribution of prime numbers, and which is mind-blowing to me. And I don't know how they found this connection, and there might definitely be a back-end explanation to why all of this is connected to the prime numbers, and such a complex mathematics to find the simple distribution of prime numbers. Thank you.
Thank you, Akshay. Now we have time for one question.